Well, hello, and welcome back to another episode of Quantitative Bites. It's great to see you. I hope you're all doing well. Today, this is probably going to be the last episode, at least for now, in this series of videos on following my work to develop a simple 2D primitives library using SDL2 and C++. I think I've kind of gone over enough. My whole objective with this short series really was to for it to be inspiring, to people out there to think about how to maybe go about writing this kind of code or doing this kind of thing for themselves, rather than being an absolute tutorial covering every detail of how to go about doing this. So this has really been more about charting my progress as I sort of go on and develop this code, and how I go about that process of doing things, rather than, as I say, rather than being a definitive tutorial. And I think, this is episode 6 now, and I think it's probably enough. I will continue to develop the 2D primitives library for my own purposes, but I'm probably not going to make any more videos about it for now. Next week I want to move on to some other things, which I hope will be at least as exciting as this has been, if not more so. So hold out for that, and hopefully that will be good. What I want to do today really is just wrap up a few things and talk about the work I've been doing for the last week. Very first thing I want to get out of the way is that I realized that there was a bug in my implementation of the FilledPoly class from episode 3. And if you look here, you can see this was the test shape that we used for the FilledPoly class originally. And it's concave and everything else, or partially concave. And I thought this was a really quite a good test. And because of that, I didn't really go on to look at a variety of other situations. And what happened was, when I came to look at implementing rotations, we're going to talk about that a little bit later, I realized there is actually a problem with this. If we were to rotate this shape slightly, as you see here, now you can see the problem. So very clearly, this has no longer rendered the shape correctly. And this was a test case that I simply didn't consider when I first wrote the code. And it's actually a really interesting one. It took me, I spent several hours, I don't mind to admit, actually going over the situation, over the code, and trying to work out not just what was going on, but also how to fix it. So it turns out that the problem occurs when there is a vertex of the polygon that corresponds exactly to the y value of one of our search lines. If you want to know, go back and check out episode 3. I'll put a link up here. Go and check out episode 3 if you want to know a bit more about what we're talking about, if you haven't seen that episode already. But where the search line, the y value of one of our search lines, corresponds exactly to a vertex, we get a problem. As you can see in this example here, so assuming we were just doing a simple triangle, when we do the search line for the center, we see that it has one intersection at the left-hand edge of the shape, but then it passes exactly through the vertex on the right-hand side of the shape. And the problem comes because, although it picks up one intersection for the left-hand edge, when it passes through the vertex, there are two edges that share that vertex. And so it will pick up two intersections there. And what that means, if we consider a point outside the shape, as we see here, when we cast that search line through, we count 3 edge intersections. And as we talked about in episode 3, if we count an odd number of edge intersections, we are considering that to be inside the shape. So we see that we start to get pixels here that are classified as being inside the shape, even though they're clearly not. Equally, if we consider a point inside the shape, as you can see here, then what we find now is that we no longer have the intersection on the left-hand edge, but we still have the two intersections corresponding to the vertex. And that means we're counting an even number of edge intersections, so these pixels are now classified as being outside of the shape, and that leads to this problem. It might seem a bit surprising. It took me a little while to pin down that that's exactly what was going on. And now I spent a long time trying out different ways of solving this by trying to avoid double counting of edges and that kind of thing. And what I found was, although you can do that, and in some circumstances that will work fine, there are always other circumstances where it won't. And what I realized is that you just end up with very complicated if, else if, then blocks of code trying to count for every possible eventuality. And there's also, along with that, not only does that make the code quite untidy, which I don't like, but also it results in a performance hit. you know, obviously. I mean, this algorithm is quite slow to begin with, really. It's not a high-performance algorithm to start with, but adding sort of a complex nest of conditional statements to try to identify every possible scenario here really just makes matters worse. So in the end, what I've done to solve this problem was actually to, in the update function for the FilledPoly class, what I decided to do is convert all the vertex positions to floating point values. They are of course originally integers because, you know, they're numbers of pixels that we're dealing with everything as integer numbers of pixels on the screen. So now what I do is convert them to floating points before we do the whole scan search lines for the intersections. And I add a very tiny vertical displacement. And this feels wrong. It doesn't feel like the right thing to do, I'll admit, but the fact is it works. And the point is that the displacement that we add is extremely small, just 0.001 or something like that. So it's a tiny, tiny fraction of 1 pixel. And it's not enough because of rounding and everything else. When we come to actually convert everything back to integer numbers of pixels, they're going to be in the same place. So it doesn't result in any actual error in our code. But what it means is that none of the search lines then correspond exactly to the y position of any of the vertices. And as improper as it seems to do it this way, it does actually work. So this is the code you can see here that I've modified. So this is from the update function or the update method of the FilledPoly class. And you can see what we're doing here. We're simply converting the vertices into floating points, and then we're adding the small displacement. We're doing the search line method to classify whether pixels are inside or outside, and well, that's it. Because the search lines correspond to the integer numbers of pixels, there's never any need actually to convert anything back from floating point to integer, because we're looping over integer pixel locations anyway. So that's really quite straightforward. And, well, that works. That fixed the problem. As you can see, here's an example of the same test shape from the beginning, rotated to the awkward angle, and we can see that it now works. We'll have a look at that code a little bit more detail later on when we go to the computer. Okay, so apart from that, what I've really mostly been looking at over the last week is implementing rectangles. And as I talked about, one thing I wanted to do was to implement lines of variable thickness, and each line segment to do that can easily be represented as a rectangle. I'm not going to specifically talk about implementing lines here. We are just going to talk about rectangles. And, you know, obviously it's quite trivial to generalize from that. So you'd think, if you initially think about rectangles, such as the example shown here, that's dead easy to do, right? All we have to do is fill in all of the pixels in the bounding box, and yay, we've got a rectangle. And that's true for this case. But what happens if you have the case like this, where the rectangle has been rotated? Still a rectangle, but in that condition, in this condition, there is no possible way that could be done simply by looping over all the pixels in the bounding box and filling them in. I mean, I suppose you could do some complicated thing of, you know, rotating the texture or something like that, and you could, but I think that sort of what I would call an image processing approach to solving the problem is really likely to be very inefficient compared to simply drawing a shape directly. So what I've decided to do is to represent rectangles as a pair of triangles, as you see here. And that, although of course for a rectangle that is orientated along the horizontal or the vertical axes, that obviously seems overkill. However, it does result in a shape that can be rotated to any arbitrary angle. And as I mentioned at the beginning, one of the other things I've done over the last week is implement the functionality to rotate these shapes, to make them rotate in things which can be used for animation, or indeed just to create more variety in terms of illustrations. So the code I come up with, we can specify a rectangle in terms of its left coordinate, its bottom coordinate, and its width and its height, and then we can rotate it to the angle that we want. So we can use that to create any particular rectangle shape that we might want in our scene, which I think is quite good and gives quite a great deal of, quite a good level of flexibility. Now, in order to make this work, I had to make some modifications to the triangle class. What I wanted to avoid was having to implement another set of code to draw triangles. And I did think about simply having the rectangle class, or the class for the rectangle shape, instantiate two members of the triangle class and then simply use those. But I felt that would be really inefficient, because then we would be storing two separate textures corresponding to the two separate triangles. And it would mean rendering a rectangle would mean rendering or blitting two textures to the screen every time. And that didn't really seem a good way of doing things. What I wanted to do was to be able to render the pair of triangles for the rectangle directly into one texture, or preferably into one pixel buffer. So what I did was I created a static method in the triangle class. We'll have a look at that when we go to the computer in a moment. That is responsible for rendering the triangle shape into the pixel buffer. And by declaring it as a static method or function, it means that we can access it from without reference to a specific instance of the triangle class, and that means that we can access it from outside. And also we move it into obviously make it a public function rather than a private function. There's a couple of other changes I had to make to support that. We'll look at that in a moment. But doing it that way makes it very easy. It means in the actual update function or update method of the rectangle class, all we need to do is we create our pixel buffer the way we've done for all of the other shapes, and then we simply call the appropriate new function from the triangle class in order to render, we call it twice in order to render the two triangles into our texture for the rectangle. And then after that, to be honest, everything else for implementation of rectangle is exactly as we've done for every other shape. So that's all pretty straightforward. And I think this is really kind of a good approach of doing composite shapes. And when I go forward, and as I say, I'm going to probably continue to develop this myself, even if I don't make more videos about it. But I want to implement a sort of generic class for composite shapes, so you can combine the different shapes together into one composite shape, which would be then stored as a single texture, which I think is a good way of doing things. And I will do that in this approach. So probably going forward, I will create static methods in all of the shape classes and actually render the shape into the pixel buffer and make those public so that they are then accessible from, I will probably create some kind of composite shape class to do that. That's sort of my thinking of where I want to go with this. And, you know, as I said, always my intention with this short series is more about inspiration than it being a specific tutorial. So, I just like to discuss what my thoughts are and where I want to go with this. And, you know, I'd be very interested. I mean, if any of you have any ideas of things that you would like to do with this, or different ways of doing things, then, you know, do let me know in the comments below. I'd love to hear from you. It's an interesting area, and I by no means have all the answers. So yeah, it'd be great to have some discussion about it. So I briefly mentioned the other thing that I've added over the last week is support for rotations. If you remember in the simple animation episode link here, we looked at translations. I've now added support to all of the shapes for translations and also rotations. It's very easy to implement two-dimensional rotations. I'm not going to talk about the maths of that. You can look that up if you're interested practically anywhere. Just Google it. There's a lot of material out there. Wikipedia has, for example, has a good article on doing that. So that's really easy, and exactly the same as we did with translations. All we have to do is rotate the vertices to a new position, and except, of course, with translations, we simply changed where we were rendering the texture, and we didn't need to redraw the shape. If we modify the vertices by, for example, a rotation, then of course we have to call the update method on the particular shape again in order to actually re-render that shape into the texture. But we'll see that when we come to the code in a moment. So really that's it for my introduction. We're going to move to the computer in a minute, have a quick look at the code. Before we do that though, I just want to say that if you like this video, please do remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. I do try to make a video once a week approximately, and like I say, after this episode, so starting next week, we've got some new material coming up that I hope will be really exciting. If you subscribe, if you haven't done so already, then you don't need to worry about missing anything. Thank you very much. Anyway, let's go to the computer and let's have a look at the code I've been working on this week. Okay, so here we are at the computer, and the first thing that I wanted to very quickly look at was the code for the FilledPoly class, where we fixed the particular bug that I demonstrated. The only change that we had to make really for that is in the update function here. So qblib2d : FilledPoly : update. And everything stays the same except for what we've done now is we've defined x3, y3, x4 and y4 as floats, whereas previously they were integers. So if you remember x1, y1 and x2, y2, these are the endpoints of our search line that we're using, and x3, y3, x4 and y4 are going to be the vertices of the current edge that we're considering. So we loop through every edge and we test for intersections with the search line. And now we're considering our the vertices for our polygon edge as floating points instead of integers. And all that we do now is where we extract previously we just extracted the vertices from mVertex list. I've talked about how we do that before, don't need to mention it again, but now we just static cast those to float. And we add, as I mentioned, a very, very small displacement to the y value, just 0.001. And as I said in the introduction, this kind of doesn't really feel the right way of doing it, but it does work. And yes, it doesn't result, I believe it doesn't result in any distortion to the shape. We still get exactly the shape we want. Apart from that, all of the rest of the code is exactly the same, except that I made a couple of minor improvements for efficiency, where I noticed that the value of y1 minus y2 is always going to be 0, because y1 and y2 are by definition the same, as we see here. So this part of the equation to compute the determinant where we multiply by y1 minus y2, we don't need to regard that because this is always going to be 0, so that will always be 0, so we can shorten the calculation for the determinant to that. And then we can also do the same efficiency here where we calculate the value of v. We can also ignore this part because here we have y2 minus y1, which is always going to be 0. And apart from that, everything stays the same, except I'd modified these to be greater than or equal to and less than or equal to for u and v, and that's it. That is everything that we need to fix that code, and as we saw in the demonstration just now in the introduction, that does resolve the problem. Now, I remain convinced that there are more efficient ways of dealing with this, of solving the problem of detecting whether or not we're inside the polygon or not. And indeed, if you Google for this, you can find numerous examples of other algorithms. I know no one that I found, no one doing it quite the way that I've approached it here. And I suspect that's because this method is actually relatively slow. However, I think it results in quite neat, elegant code, and I quite like it. And you know, from the outset, I've not been going for real time with this library, so I think that's okay. Okay, so the other thing I wanted to talk about, in order to implement the rectangle class, I made some modifications to triangle. So let's just have a look at that first before we go to the triangle class specifically. So all that I've done is I've created a new function or a new method in the triangle class called renderTriangle, and this accepts as input a pointer to the pixel buffer, the two arrays corresponding to the three vertices, the x and y coordinates of the three vertices, a rectangle, an SDL rect structure for the bounds, and a QB color object for the color. And the important thing to note is that this function is declared static. It is in the public section of the class, and it is declared static, which means that we can access it without having to refer to a specific instance of the triangle class. And then in triangle.cpp, the only change that I've made, what I've done previously, we did all the code for rendering the triangle was in the update function, or the update method. And what I've done now is move that here to the new function called renderTriangle. So all we do now in update is we call renderTriangle, we pass to it temp pixels, which is the pixel buffer that we create the normal way, m_vx and m_vy are our vertices, mBounds, of course, is our bounding box, and mColor is the color. So if we then look at the new function, renderTriangle, we don't need to talk about that very much. That is simply pretty much exactly the same code that we had before, except now, of course, it can't make use of any member variables belonging to the class because we need this function to be callable without reference to a specific instance of the class because we've declared it static. So it has to only use variables that are passed to it in the function declaration. And then it just does, other than that, it's exactly the same as the code that we went over before, so I'm not going to talk about that again. But that is really the extent of the changes I made to triangle. Okay, so let's have a look at rectangle. This is the new class, rectangle. So rectangle.h, this is exactly the same structure as for every other shape, so I'm not going to talk about it a great deal. The one thing we introduced now that's new is we have for all of the shapes a virtual void rotate. That is in the object base class as well. In fact, if we look at object.h, so in object.h we see we've declared the virtual void rotate float angle, so that we have to implement that then for every shape. So in rectangle.h we have the declaration for that there, and that's it. And then private member variables we store. Now this is something I've now done for every shape. I store 2 copies of the vertices. It does seem a little bit inefficient, but I think the extra memory is worth it to save the performance hit of having to do the conversions between integer and float all the time. So we store 1 integer set of the vertices. Remember, the user has to specify the position of the shape in integer coordinates. And we also store a floating point set. So if we look at rectangle.cpp, we see in the constructor, so this is exactly the same form as the constructor really for other shapes, but we're specifying, so the rectangle is specified in terms of the left, bottom, width and height, so it just passes integers. We're not using any SDL structures for that. And as before, we store the vertices in m_vx and m_vy, but also we then convert those here in the constructor to store the floating point version. So we only have to do this conversion to floating point once, and we store m_vxf and m_vyf. And then pretty much everything about this code is the same as we've done for other shapes. Computing bounds, that's the same as for triangles. Translate, that's the same as we've seen before. Rotate, I'm going to come back to that in a moment. And update, so this is the function that actually is responsible for drawing the rectangle into the texture. And we see this piece of code is common to every shape, that we allocate memory for the pixel buffer and we set all the bytes of that to 0 to clear it. But now what we need to do, instead of rendering our shape directly, we're going to generate 2 triangles. So we convert the 4 vertices of our rectangle into 2 sets of 3 vertices corresponding to the triangles, which we call Vx1, Vy1, and Vx2 and Vy2. That's pretty obvious. I'd leave you to look over that. It's not complicated. And then we're using the render triangle function or method from the triangle class. So we use qblib2d : triangle : render triangle, and we pass to it temp pixels, which is our pointer here to our pixel buffer, Vx1, Vy1, m bounds and m color, and then the second call we pass Vx2 and Vy2, but otherwise it's the same. So the effect of that will be to render the 2 triangles into the pixel buffer that we've created for the rectangle, and then as before we simply use SDL update texture to copy the contents of that pixel buffer into our texture, and that's it. Everything else there is exactly as we've seen for every other shape class that I've implemented. Okay, and the one thing I want to mention just about the rotate function, so this is now something I've added to every shape that allows us to do rotations for animations. And so what this does, at the moment it calculates the center of rotation as being the center of the bounding box. Now there are problems with doing that because the dimensions of the bounding box can change for some shapes as they rotate, so that does cause a problem. I'm not going to leave it at that. I'm going to probably allow the user to specify where they want the center to be, or to calculate it automatically as being the center, or the mean of the vertices, the mean position of all of the vertices. But that's to do in future. But the basic principle is sound. So we calculate the center point, r center x and r center y, and we're then going to loop through and apply the rotation to all of our vertices in order to save a little bit of time, because we're using sine and cosine functions from math.h. We calculate sine theta and cosine theta in advance before entering the loop. It just saves a little bit. We then calculate a normalized x by taking the floating point version of the vertex and subtracting the center location, so that gives a floating point. And we then calculate the new x location by taking, we do the same for y, sorry, okay. And then we calculate new x and new y simply using the standard implementation of 2-dimensional rotation. You can look this up easily yourself. There's a good Wikipedia article actually on how to do this. But it's quite straightforward. So we simply do the new x is equal to norm x times cos theta minus norm y times sine theta, and new y is equal to norm x times sine theta plus norm y times cos theta. It's pretty straightforward. And we then simply, because we subtracted the center point before doing that, we then just have to add the center point back on before we store the new position of the vertex. So that's pretty straightforward. And then, because we've done everything there on the floating point versions, we then simply update our integer versions by simply static casting and to int and then rounding off those values. And that's actually it. And then because we've modified the vertices, we have to call compute bounds again. And of course we have to call update to cause it to recalculate the texture. And that's it. That's the basic functionality for implementing rotations. Now, the reason to work on the floating point versions of the vertices, and actually this is another problem that took me quite a while to get to the bottom of, if you're implementing, if you think about it, a very small rotation, if you want to make a smooth animation, you want the steps of the rotation to be very small. And if when you apply that rotation, it doesn't result in an integer value of difference to say one of the vertices or to all of the vertices, then because the vertices are stored as integers, they won't change, they won't move. So you'll end up with an effect, say maybe you'll apply a small rotation and absolutely nothing will happen, the shape will just stay exactly the same, or perhaps one or two vertices will move but the others will stay. It will depend on rounding errors. So by storing a floating point version of the vertices and applying the rotation to those and ensuring that we store the new floating point version, it means that we can apply any rotation angle that we like. And the conversion to integer only really affects what happens when we come to actually try to render the shape to the window, which I think is quite a neat way of working. It's a little bit inefficient perhaps in terms of RAM storing two sets of vertices, but I mean for a rectangle or for a triangle, you know, if the triangle has only 3 vertices, the rectangle has only 4, so it's not a big deal. And I think storing them permanently as that, you know, saves the performance hit. Plus it also, in fact, actually, I'm not sure that there's necessarily any other way of doing it, because we always have to apply the rotation to the floating point version. So we need to store what the floating point version of the coordinate was without the rounding error introduced by rounding it off to an integer. So actually, I do kind of think it's probably really the only way to do it. Okay, and that's it. I've gone and implemented rotate exactly the same way for all of the other shapes. So we've looked at how to do that before with triangle. The basic principles are exactly the same. So I'm not going to really talk about that. What we're going to do, though, is just have a look. If we just compile our code, well, it's already compiled already. If we run that code and we see here, this is an instance of the rectangle class, and we see how we can implement that by implementing that as two triangles, we create a rectangle that we can rotate to any arbitrary angle, which is quite useful. Triangle, of course, is as it was. Now the triangle, if you watch it closely, you will notice it moving around a little bit because the center point changes, and so I do need to fix that. And this is the corrected FilledPoly code, and now you can see that we can rotate this shape as well to any arbitrary angle without having any problems. And there we go. That's really everything I've been working on over the last week. Okay, so that's really everything I wanted to talk about this week. I really hope you've enjoyed this episode. It's been a great deal of pleasure making it. In fact, the whole series, as I said, this is probably the last episode I'm going to do for now in this series on the 2D primitives library. So I really hope it's been useful to you guys. I hope you've managed to get something out of it. I hope I've managed to inspire at least some of you about some things to do, or, you know, how to go about you know, solving this kind of problem for yourself. And yeah, you know, I mean, let me know in the comments below what you think. Let me know if you have any other ideas for things you might like to see included if I go on to do any more episodes or a future series on 2D primitive shapes. Maybe I'll think about including those, but do let me know in the comments below what you think. It would be great to hear from you. As I say, next week we're going to move on to something quite different. Which I'm super excited about. So you know, I hope that will I hope that will be of interest to you as well. I think it will be. I think it's kind of cool. I'm not going to say too much right now. You're just going to have to wait until next week to find out what that will all be about. Anyway, that really just leaves me to say, you know, thank you very much for watching, and I really hope you've enjoyed this video, and I really hope you've enjoyed all 6 episodes of this short series. You know, as I said at the beginning, if you've liked this video, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos, especially with exciting new content coming up next week. Anyway, that just leaves me to say thank you very much for watching, and I really look forward to seeing you next week. Bye.